What's up, grade 11s? It is a Tuesday and you're hanging off with Looney and the other cool Tracy. We've got two Tracys, so this one is the other one, hey? The cool one. Tracy, how are you doing?
I'm well, thanks, Looney. How are you?
I'm good, thank you. So what are we doing for the grade 11s?
Grade 11s, we're doing mole calculations again. So we're going to take this further. We did introduce the concept last week, and this week we're going to be working on mole calculations and specifically looking at empirical and molecular formula, at limiting reagents. It's going to be a great lesson.
All right, I'll send you to your board just to get ready.
Thanks so much.
Grade 11s, you heard it, mole calculations. I remember the section back in the day when I used to do physical sciences, and it used to mess with my head a bit, but don't you sweat it, guys. You do have Learn Extra Live for just that. Remember, you can hit us up on Twitter, at Learn Extra. On Facebook, it is facebook.com/Learn Extra. Remember, you guys can also download show notes, video schedules. You can also see how to order books and DVDs if you want more revision material, past papers, exam papers, just to get you guys prepped up for the upcoming exams. It is all on learnextra.co.za/live, where you get all your information you need, guys, for how to just be a better student, you know, and be hooked up with all the Learn Extra Live stuff. Remember, we've got so much going on today, guys, but I will tell you later on during the show. So right now, I'll take it straight back to Tracy.
Thanks, Looney. So grade 11s, what are we covering today? Mole calculations. It's our second session on mole calculations. And in this lesson, we're going to revise a bit on mole calculations, because these mole calculations are incredibly helpful, incredibly useful. Almost certainly you will get one of these type of questions over the course of your science course. We're going to discuss limiting and excess reagents. Now, that's going to come into it as well. And then we work out on percentages, percentage purity as well as percentage yield. Okay, and we're going to solve problems relating to empirical formula and molecular formula. So let's get straight into it. I want us to recap a little bit about what we've done so far. We have looked at a number of equations that help us to calculate the number of moles. So when you're working with masses, you've got number of moles is equal to mass divided by the molar mass. Okay? And that molar mass you would work out from the periodic table. You'd go and get the relative atomic masses and work out the mass of the compound, and then you can take it from there. The next one, this is volume, and it's volume specifically when you are working with a gas or many gases. So number of moles here, once again, we've got number of moles. V is standing for the volume of your sample. And this one is the molar volume, the volume of 1 mole of gas at STP, okay, at standard temperature and pressure. And last one, the concentration. Here we've got C standing for concentration, N standing for number of moles, and V is for volume. And this is the volume of a solution. Okay? So be very cautious that you don't mix up the volume when we're speaking about gases and the volume when we're speaking about the concentration of the solution. That's the volume of how much liquid you've got as the solvent. All right? So make sure that you've got these three equations and you've got them in your toolbox. You know when to pull them out. Last thing we discussed last week, is to consider a balanced chemical equation. Now, it's very, very important that you always deal with a balanced chemical equation, and I would highly recommend that when you've got an equation, that you first, before you go into it, check that it's balanced. Because that balanced equation is going to help you in terms of comparing number of moles of two reactants or a reactant and a product, okay, or two products for that matter. It's going to help you to work out the mole calculations that we're going to be dealing with, all right? So it will give you the big numbers in the front, all right? Those big balancing numbers are going to provide the mole ratio of the reactants and the products. And I'm going to highly recommend to you that what you do with these is that you take the mole root. So maybe you're working with the mass of something, okay? You're going to convert that mass into a number of moles, okay? Then via the mole root, as in this mole ratio comparing, you're going to be able to compare the mole ratio and work into the number of moles of your second substance. Once we've got that number of moles of the second substance, we can convert that, maybe it's to a concentration, okay? Or it could be to work out a volume if it's a gas. Or we could work out the mass. Whatever you're going to do with any of these stoichiometric calculations, I would highly recommend that you convert first to number of moles. And how do you do that? Well, we've just gone through those three equations at the start. So, whether it's a mass, or our input here could be a volume, or our input could be a concentration. Okay? The idea is the same. Convert to number of moles. Okay? Then compare with the mole ratio. Maybe it's a 1:1 ratio, maybe it's a 1:2 ratio, or any other type of ratio. Okay? We're going to compare with the mole ratio, get our second substance into number of moles, and then work out whatever we need to answer the question. So let's get straight into one of the questions. And I've got here question 1. Let's have a look at it. Given the following reaction, and here we are, 3NO2 plus water forms 2HNO3 plus nitrogen monoxide NO. First thing I want to notice before we go any further is to notice these are all gases. They're all in the gas phase, right? How do we tell that? Well, we get given those little small g's, which means this is all in the gaseous phase. Next, if 2,7 cubic decimeters, dm cubed, of NO2 is used, what volume of HNO3 is produced? Okay, so I want us to just go through what we've got, and I'm going to take off these little circles because I've noted that they're all gases, and what that's going to tell me is that I can work firstly with the number of moles is equal to volume over the molar volume. So we get given a volume here for nitrogen dioxide. So immediately I'm going to actually rewrite this equation because I'm certain that when you start on your piece of paper, you're going to want to have the equation written at the top of your page. Okay, there's our reaction, our equation, HNO3 plus NO. You've got that spaced across your whole page. Now we need to look at what we're being asked to do. We've got a volume here. V is equal to 2.7 decimeters cubed. Okay? I'm putting that information directly underneath nitrogen dioxide. And my question is, what volume of HNO3? So next, underneath this one, I'm putting volume equals question mark, because that's what I'm going to want to find. Now, what did we say about the mole calculations? Mole roots convert to number of moles, and then we can compare. So let's do that first. Let's go across here. Number of moles is equal to volume divided by the molar volume. Let's give ourselves some space to write. What volume did we have? We had 2.7 decimeters cubed, and we are dividing here by 22.4 decimeters cubed. Why is that? Well, it's because for 1 mole of gas at standard temperature and pressure, the volume is going to occupy 22.4 cubic decimeters of space. So it's a helpful number to have. It's on your data sheet. You would go and work with that molar volume, and we're going to get an answer. Now let's find our calculator and work it out. It was 2.7 divided by 22.4, giving me my answer. Let's have it as a decimal, 0.12. So going across here, 0.12, and it's going to be moles of NO2, right? Because that's what I was working with. Now, I need to get from NO2 all the way across to HNO3. So how I'm going to do that? I'm going to compare with the mole ratio, right? So let's take this down and work with my mole ratio. What does the balanced equation say? The balanced equation says it is a 3:2 ratio. So I'm going to write that down. It is a 3:2 ratio, which means it's going to be 0.12 moles is to, how am I going to work that out? Well, firstly I need to divide by 3, and then if I want to move across to that side, multiply by 2. So, going back to my calculator, 0.12 divide by 3, multiply by 2, and that's going to give me an answer, 0.08. So, is to 0.08, and the unit here is moles. But now what? Moles. Moles of what? Moles of HNO3. Go back. That was what I'm working with. So the big jump from the one substance to the other substance, the only way I can compare them, the only way I've got information about both of them, is the ratio, the mole ratio that we're working with. Right? So I've got the mole ratio here, and this is of HNO3. Now, I can work out what I'm asked to work out, which was, what is the volume, I believe. Let's go back and check the question. What volume of that is produced? It was also a gas, so I can still work with that same equation. Number of moles is equal to volume divided by molar volume. Let's rearrange it. Volume would be equal to number of moles multiplied by the molar volume. And I'm just writing that, showing that we're taking across from a denominator, it was dividing, we take it across the other side, it's now multiplying. So 0.08 multiplied by, and what is the molar volume? It is 22.4 cubic decimeters. So 22.4 would be equal to the volume. So volume's answer, let's go and work that out. It's going to be multiplied by 22.4 equals 1,792. So going back here, 1,792, and let's round that off, 1.79 decimeters cubed of HNO3. Okay, that's the final answer in terms of what is produced. Let's go back and work through exactly how we worked that out. We first observed the balanced chemical equation. Then what we did was we converted whatever information we were given to number of moles. So we had a number of moles that we could compare via the mole ratio. So I'm going to just, in a separate color over here, write up our plan of action. Volume, I converted to moles. Once you've got moles, you can compare and get the moles of the second substance, the other substance. And then we had to answer the question, and we took that back to a volume. It's quite helpful just to have a plan of action in mind in terms of how you're going to work this through. And when we're going to come back from this next break, we're going to look at limiting reagents and comparing some more of these types of questions. But it's so vitally important that you always follow through all of these types of questions and think through what you're doing. Convert to moles, compare the mole ratio, and then work out your final answer. I'll see you in a moment, grade 11s. Over to you, Lenny.
All right. Mindset says we are going to take a very short break, but don't go anywhere. Stay glued to your screen, guys, because the After Earth trailer will be playing. You'll see Will Smith and his son, doing their thing, kicking some animals there, and all of that. Action-packed, guys. Remember, we do have competition running. I will tell you more information straight after the break. Welcome back, Mindsetters, from that very short break. I hope you guys are just as excited as I am about After Earth. So basically, it's a futuristic movie, and we've got this competition running. It opens in cinemas on the 7th of June, guys. 7th. This coming, I think Friday. Yes, this coming Friday, it comes out. So remember, guys, all you need to do in order to stand a chance to win those 2 tickets and these amazing prizes from the goodie bag is go on to learnextra.co.za/After Earth and enter your code word. For grade 11s, your code word is respiration. All to do with the breathing and all of that. Respiration, guys, that is your code word. Stand a chance to win yourself this nice sweatband, sweat. It's got a nice little zip over here, guys, so you can put in some money and all of that. So, this cool pen, guys, check this out. It lights blue. It's got like blue light when you click it. It just blue light appears out of nowhere, guys. So awesome. There's this notepad as well. It's a great notebook for you artists out there, for people who like to write. It's written After Earth. It's all personalized stuff from After Earth, the movie, guys. We also have the t-shirt. So it's a great goodie bag with those 2 tickets. All you need to do is go to learnextra.co.za/After Earth, enter respiration, and remember, guys, the competition does close at 12 p.m. tonight. So after 12, sorry, you can't enter because it's done, it's over. Okay? Remember, guys, I will post all the information that you do need on our Facebook page, and I'd just like to congratulate our winner here. Let me quickly just check. You have won yourself 2 tickets to go see After Earth. So let me quickly sorry, guys. My word. I'll tell you the winner shortly, guys. But you have won yourself 2 tickets to go watch After Earth. It's Kylex Ruland. I've just forgotten the surname, but I will post it on Facebook, guys. Remember, all the information you need is on Facebook for After Earth. So let's take it straight back to Tracy with those questions that we had.
Thanks so much. Grade 11s, I'm seeing a few questions on the Facebook page asking me, where did I come up with a 22,4 decimeters cubed? And that is the molar volume. Okay, so the idea behind this is that at standard temperature and pressure, you possibly have worked through this equation, PV is equal to nRT, okay? What we have solved for V would be nRT divided by pressure, okay, divided by P, taking into account if n was 1, that's your universal gas constant, T is standard temperature, P standard pressure. So they have worked out that at standard temperature and pressure, the volume of the gas happens to be 22,4 decimeters cubed. So if we've worked out what that volume is for 1 mole of gas at those standard conditions, then we can use it to work out any number of moles, right? So you would have the volume of the sample divided by 22,4, which is the volume that 1 mole of gas takes up. And I hope that answers your questions. Join with me as I now move across to limiting and excess reagents. A limiting reagent is completely used up in a chemical reaction, and that makes sense in terms of what the wording means. Limiting is referring to holding something back, okay? It limits something going any further. And what actually happens is that in a limiting reagent gets used up completely. So there is no more of it to react any further, and so it holds up the reaction from going any further. Nothing more can be produced because this thing is finished. It's used up. By comparison, an excess reagent, okay, is not, underline the word not completely used up in a chemical reaction, and so therefore we can say it is there is extra of it, okay? It is in excess. There is more of it that can't be used any further because something else is used up, limiting. Okay, we'll do a question on this in a moment. Next, we want to talk about percentage yield. And by percentage yield, we are working with always a percentage, okay? Just like if you get a percent for your science test, you get your mark divided by the total mark multiplied by 100, okay? When I say the total mark, the total maximum that you could have gotten. In the same way, we've got this equation for the percentage yield. Now, yield is the amount we're going to get out, okay? So I could go and work out through my chemical calculations, like we've done in the past, I could go and work out from those chemical calculations. Let's just write that, let us see slightly better. From those chemical calculations, I can work out theoretically what we should get, okay? The theoretical yield, how much we should get. But in practice, okay, actually in a science lab, some of the substances won't react, okay? So we have then an actual yield. So it's the actual yield divided by theoretically the maximum we could have potentially gotten out, okay? So that divided, multiplied by 100 is going to give us the percentage yield, how much we got out, okay, as a percentage. Let's get cracking into some of these questions, because I know that's what is going to help you as you look into so many of these ideas. Ozone reacts with the nitrogen monoxide gas to produce nitrogen dioxide gas. The NO gas forms largely as a result of emissions from the exhausts of motor car vehicles and from certain jet planes. The NO2 gas also contributes to that brown smog, the smoke and fog, which is seen over most urban areas. This gas is harmful to humans, so we're talking air pollution, very important. This gas is harmful to humans as it causes breathing difficulties, respiratory problems. The following equation indicates the reaction between ozone and nitrogen monoxide. So we get this equation. In one such reaction, we've got a value. 0.74 grams of O3 reacts with 0.6 grams of nitrogen monoxide. Calculate the number of moles. Now, first thing I want you to notice here is we've got two mass values. We've got a mass of O3, and we've got a mass here of nitrogen monoxide, NO. We've got two masses, and the question is, which one do we start with? Well, we've got to pretty much work with both, and we're going to compare them and see which one is limiting and which one is in excess. The reason we want to do that is because not all of the substance will react. There will be some that is in excess that is left over. Okay, so it's very important to compare these two, and the way I'm going to do that, and that's going to tackle question A. Calculate the number of moles of each of them present at the start of the reaction. And then part B of this question is asking us to identify limiting reagent and justify our answer. So let's get into tackling this question. Once again, I think it's very helpful for you to write down your equation, NO, and this forms, let's just undo that. This stuff forms NO2. let's just check it quickly that we've got the correct equation, plus oxygen plus O2. So you might notice, well, I look like I'm cramming that in on the side. It's specifically because I want us to compare these two substances, the ozone, the O3, and the NO, because that was what I was given information about. Here I was told the mass of ozone was 0.74 grams in the question. Go back and check it. 0.74 grams and 0.67 grams. And this one's mass was 0.67 grams. I'm pretty much working with half the two halves of the page as I work this through, because what I'm doing is I'm going to compare them. So what do? Whenever we've got masses, we're going to convert to moles, and that's going to help us to calculate. So let's go over here. Number of moles is equal to mass over molar mass. So first I need to work out the molar mass of ozone, O3. And it's going to be 3 multiplied by 16. Where do I get that number from? Let's go across to a periodic table. There it is, oxygen, and its relative atomic mass is the bottom number. So that's the 16 over there. Okay. Coming back here, we've got 3 times 16. We'll go across here. 3 multiplied by 16 is going to give us 48. So the molar mass is 48 grams per mole. Okay. Now I can work number of moles is equal to mass over molar mass, and we had 0.74 divided by 48. Let's go back here. Recognize where I got each of the numbers from. That's going to give me, on my calculator, 0.74 divided by 48, the molar mass, is going to give me 0.015. 0.015 moles of O3. Now you might want to ask, why do I always write of whatever substance? Well, it's because specifically now I'm going to be comparing these substances. I'm going to be comparing the ozone and comparing the nitrogen monoxide. So I've done the first part, which was calculate the number of moles, but only for ozone. Let's go back and do the same for nitrogen monoxide. So I'm going to just choose a different pen color so we are on track. Molar mass, good place to start, of NO. And that's going to be equal to, find my periodic table. Well, nitrogen is over here, 14, and oxygen, 16. So going back, we've got 14 plus 16 is going to give me, hopefully you can do that in your head, 14 plus 16 is equal to 30. So we've got there 30 grams per mole, right? Now, grade 11s, what I've got is just the molar mass. I need to take this to moles. So, once again, number of moles is equal to mass divided by the molar mass. And let's bring this down. What was the mass of this sample? The mass of this sample was 0.67 grams. So we've got there 0.67 grams divided by 30 grams in 1 mole. So back 0.67 divided by 30 is equal to, write it as a decimal, so 0.022. I'm keeping quite a few decimal places here. 0.022 moles of NO. Now what I want us to do is compare these two numbers. We need to work out which one will be limiting and which one will be in excess, right? Limiting means it's going to run out, right? Excess means there's going to be extra, okay? So first, before we actually just look at the numbers, I want us to go back to this equation. And I'm going to go back to the original equation and just check with me. We had no balancing numbers in the front there. Check it quickly. Oxygen, there are 3 plus 1 is going to give me 4 oxygens on the left-hand side. 2 plus 2 is also going to give me 4 oxygens on the right-hand side. And 1 nitrogen, 1 nitrogen. This thing is balanced. Okay? That's a very helpful thought to notice. So actually what we've got is a 1:1 ratio. Okay? It's balanced, and that was the ratio between the two. That means that of these two, they're in a 1:1 ratio. So which one will run out first? Well, particularly if you've got lots of numbers as decimals, if they sometimes are harder to read, take the one substance and divide it into the other substance and see what you get. Okay? And I can have a look here and say, look, that is 1 and that is to 2, and notice they're in the same number of decimal points away. So definitely this thing, the ozone, is limiting. It's going to run out. Okay? Whereas there is more nitrogen monoxide, so there's going to be extra of that left over. Okay? And that's answered part B of the question. By comparing the number of moles and comparing the mole ratio, that's how you've answered that question, and you can justify your answer. Okay? Part 3 of this question asked us to calculate the mass of NO2 produced from the reaction. So going down, we've once again got to look at a mass. And a mass of what? Well, it was NO2. So once again, I need to go back to the top, to my equation, and say, okay, now I'm looking at the stuff that's produced. And the stuff that's produced is also in a 1:1 ratio. The question is, which substance are we going to be working with? We need to be working here with specifically the ozone, because that's what's going to run out and then stop any further reaction taking place. Okay, because it's going to run out, nothing more can take place. So when you compare these, once again you've got your equation, O3 plus NO forming NO2. Was it plus O2? Okay, check it, yes. We now need to work with the mass of this, okay? But in order to do that, we have to work with a number of moles. So number of moles here was 0.015 moles. And that is the maximum number of moles we had for ozone. So we can't go any further than that, right? So here we've gone, if I just go back to our planning, we've gone moles. Now it's going to be the same number of moles, and then from moles I can convert that to a mass. Notice that this is taking place through my mole ratio, which I have seen is a 1:1 ratio. So 0.015 moles is to 0.015 moles of NO2. That's how much nitrogen dioxide can possibly be produced. Okay, so because that's the amount of ozone that I have. In the same way, now I'm going to work out the molar mass, because I want to use this equation. Number of moles is equal to mass over molar mass. Let's rearrange it. Number of moles multiplied by molar mass is going to give me the mass. going to give me the mass of the substance. My number of moles is 0.015. My molar mass, well, that's something I need to quickly go and work out. So on the side, maybe over here, molar mass of NO2. Well, nitrogen previous in this question, I found on the periodic table it was 14. Oxygen was 16, but hold on, we've got 2 of them. Okay, so I've got 14 plus 32, and on my calculator, 14 plus, if you'd like to, you could do this in brackets, 2 multiplied by 16, because there was 2 oxygens, is giving me 46. So this was 46 grams per mole. Now I can come back here, and I don't have that much space, so I'm going to rewrite this. N times molar mass is equal to mass. So the mass is 0.015 multiplied by 46, which will give me in my final answer, sorry, wrong one. Let's just go back here, grab my calculator, multiply by 0.0, sorry, just go back a sec, 0.015. Okay, and that's giving me 0.69. Write down our final answer, 0.69, and the unit is going to be in grams. So grade 11s, that was a long question, but limiting and excess reagents are very important for you to understand as you work through these. Looney, over to you.
All right. Kylex Roland Vogwe. There you go. That's the name. Congratulations. You have won yourself 2 tickets to go watch After Earth. So remember, if you need a friend, and you're just confused who you want to take, +1. Kylex Roland Mvokwe, you have won yourself those 2 tickets. Congratulations to you. Your tickets will be on their way to you. Okay, Mindsetters, we are going to take a very short break. After the break, I'll tell you more about Korea and Daba, so do stay tuned. Welcome back, Mindsetters, from that very short break. Like I said before the break, I'll tell you about Korea and Daba. So it's happening from the 20th till the 22nd of June, this month, guys, this month, at the Santon Convention Center here. So remember, guys, all you need to do in order to be there and to actually see Mindset and to go view stuff about the career choice you want to take is go on to careerandaba.co.za to register. You register for free, guys, so register yourself, your friend, your cousins, their cousins, other family members, grade 10 to 12. Remember, go register yourselves, guys, and you can get more information about the career path you want to take, and we will be there. So if you want to meet all your favorite Learn Extra Life presenters, I'll be there, Abram will be there, we'll see Indy and all the other guys. So if you just want to go there, guys, go Korea and Daba, Santon Convention Center, 20th till 22nd of June. We will be there. Ask us any questions, guys, about the career path you want to take. There will be extra information and more material on what you guys can do and advice if you're stuck on what you want to become when you're older and all of that, what you want to do after school and all of that. It's a great place to go, guys, to get all that information. Once again, I'd just like to congratulate Kylex Roland Mvogwe for winning those 2 tickets to go see After Earth. Remember, guys, about Korea and Daba, I will post all the information you need on our Facebook page. All you need to do, facebook.com/learnextra. You'll get all the information there about After Earth, Korea and Daba, and everything else you want. Just go onto Facebook. Tracy, let's do it again.
Thanks so much, Leni. So grade 11s, we've been tackling the whole idea of mole ratios and some stoichiometry calculations. I want us to do one final one, and that is empirical molecular formula. Now, it's important just to understand what we mean by empirical formula. An empirical formula is the simplest ratio of the elements in a compound. Okay? Now, when we say the simplest ratio, it's going to make more sense if I speak about the molecular formula. Now, the molecular formula is, by comparison, the full formula. Okay, so I've got two examples here. I'm going to tackle the second one first. This is propene. Prop because there's 3 carbons in the longest chain, and ene because it's a double bond between the 2 carbons. And I've just kind of sketched that out. Have a quick look here. We've got carbon with 3 carbons and 6 hydrogens. Count them with me quickly. 1, 2, 3, 4, 5, 6. And so that would be a quick schematic sketch of how these could be arranged. A simplified drawing, obviously, but that is going to be propene. Now, its molecular formula has the exact numbers, right? 3 carbons and 6 hydrogens. Its empirical formula is only the simplest ratio. So what would the simplest ratio be between these? Well, it would only be CH2 because there are twice as many hydrogens for every carbon. So we are simply looking here at the simplest ratio between them. By comparison, the molecular formula tells you the exact numbers or ratios of atoms, exact numbers of atoms in every substance, in each compound, of each type of atom in each compound. Lastly, quickly, percentage purity. You sometimes will get questions on percentage purity. Again, it's a percentage, so something divided by a total multiplied by 100. And we are speaking about the purity of the substance, how pure it is. And then you're going to have the mass of a compound divided by the total mass. I'm just writing in that word total, the total mass of the sample. So maybe you're going to get some gold out of a sample of rock. What is the mass of the gold divided by the total mass of the rock multiplied by 100? And that would get you your percentage purity of how much the percentage purity of gold in the sample. Let's go across and work on some questions based specifically on empirical molecular formula. So let's go. Question 4. Glucose. One of the sugars in the body has the following percentage composition. That's helpful. 40% carbon, 6.7% hydrogen, and 53.3% oxygen. Determine the empirical formula for glucose. So empirical formula, you're thinking simplest ratio. Right? Then part B, determine the molecular formula. Well, let's go for it with our empirical formula first. I'm going to start out by writing at the top here, carbon, hydrogen, oxygen. For carbon, I want to work with, we were told that 40% of this mass is carbon, 6.7% of this mass is hydrogen. Check us. 40% carbon, 6.7% hydrogen, and oxygen was 53.3% oxygen. Well, what does that mean? Well, it's a percentage, so it's meaning of 100. Okay? So rather than working with a percentage, we want to say, well, therefore, in 100 grams, you're going to have 40 grams of carbon, 6.7 grams of hydrogen, and 53.3 grams of oxygen. So your first step is to work from percentages and jump straight into, therefore, in 100 grams. Okay? Now I'm going to take that out. I think I'm going to just move these a sec. So we've got a little bit more space. And we had carbon there, and it was 40%. So now I'm going to work with in 100 grams. Therefore, I would have 40 grams would be carbon, 6.7 grams would be hydrogen, and 53.3 grams would be oxygen. Always, I want us to work into number of moles, remember? So what we need to do next is convert this to number of moles. And my equation, number of moles, is mass over molar mass. So my next line, I need to say, okay, what would be the relative atomic mass of each of these types of atoms? Well, it's going to be 12 grams in 1 mole. So 12, where did I get that? Going across to the periodic table, we have, and let's choose a different color, let's go with green. Carbon is 12, oxygen is 16, and hydrogen over here, 1. Now obviously you're going to use your periodic table that you've been given. This one doesn't have any decimals, but go with the one that you've been given and you would work with. So 12, hydrogen was 1, and oxygen was 16. Notice that I've actually already pretty much worked out this formula, because 40 divided by 12 will give me the number of moles. So let's do that. Give ourselves some more space. And on the side here, clear that away, 40 divided by 12 grams and 1 mole will be equal to 3 with a whole bunch of 3's recurring. So let's write it here, 3, 3, 3 recurring. 3, 3 recurring moles. Next, we're going to go with hydrogen. So I'm just drawing little dotted lines down the side here so we know what we're working with. For hydrogen, it's going to be 6,7 divided by 1, which is equal to, well, I hope that you would recognize that that's going to be 6,67. And again, recurring, sorry, it would be 6,7 moles of hydrogen. The last one, 53,3 grams divided by 16. So let's go 53.3 divided by 16 for 16 grams and 1 mole, and we get 3,33. So once again is equal to 3,33 moles of oxygen. Now notice that what we're trying to do is look at the mole ratio, and we're going to compare how many moles of each must have come in to combine to form the substance. I've got quite a few numbers here, and what we want to do is always take the smallest number and divide that in, because we want to get 1 is to something is to something. So I'm going to pick the smallest because that's recurring. Let's pick oxygen. I'm taking that number and dividing it by itself. So divide by 3,33, and that's going to get me to 1. Okay. If I divide this side by 3,33, that's going to get, sorry, that looks like an 8. Let's go back here. 3,33. Okay. And that would get me to a 2, approximately. Okay. And this last one, divide 3,33, and that's going to get me to 1. Now, what do you notice is that we're working with a ratio here. Okay, so what can I say about this ratio? Well, it means that it's 1 carbon is to 2 hydrogens is to 1. The ratio was a 1 is to 2 is to 1 ratio. Okay, so let's take that now, that ratio, that simplest ratio, and get it into a formula. What we need to do is then write our final formula, and it's going to be carbon with a little 1, hydrogen, 2 of them, and oxygen. And that there is my empirical formula. Okay. Next we need to move on and answer the second part of the question, which was what was the molecular formula? Okay. So coming along, determine the molecular formula of glucose. Now, the molecular formula is the actual formula with the exact number of each substance. Of glucose, and given that the molecular mass, next part of the point, very important, they tell us what the molecular mass actually is. So, going to the end of this question, I've got the empirical formula. Let's go and work out the molar mass of this stuff, CH2O. Now, because we've worked with it already, I know what these values are. I don't need to go and look them up. Carbon was 12. Hydrogen, 2 of them, 2 multiplied by 1, plus 16. So, go across to our calculator, add those up. 12 plus 2 plus 16 is equal to 30 grams in 1 mole. So therefore, if actually I know that this molar mass of glucose was actually 180, how many times does 30 go into 180? It goes in 6 times. So my final answer here must be that I multiply by 6. So C6H12O6. And that's the final molecular formula. Grade 11s, I hope that's really helped you. God bless for your exams. I pray they go brilliantly, and I really hope that's helped. Luni, over to you.
All right. Thank you so much, grade 11s, for tuning in. Everything of the best for your upcoming exams. I hope you guys do great. Like Tracy said, God bless you guys. Enter the competition and stand yourself a chance to win these great prizes. Until we see you again, guys, it is a goodbye from us.